Welcome back to this course in polymer chemistry. In last lecture, we started our discussion on polymer properties and their evaluation. And in last lecture, we discussed mainly mechanical properties, the stress strain behavior in tensile testing. We also discussed the other testing behavior like impact testing and flexural testing or bending testing. At the last part of the lecture, what we discussed was the relationship between the mechanical properties and chemical structure or polymer chain properties, and we found that in general flexible backbone, if you have a flexible polymer chain backbone, obviously if I want to write here, if you have a flexible polymer chain backbone, then it is easier for somebody to apply stress and deform. Now, which basically gives lower modulus, lower strength. However, the same flexible behavior can be helpful in case of impact properties, where if you impact, because of its flexibility, it can absorb that impact energy more effectively and gives you a higher impact strength, or it does not give a brittle fracture on getting hammered by a impact or hammered by a load. So flexible backbone gives lower modulus and strength, and chain stiffness of the backbone and the bulky side groups increases modulus and strength, which is self-explanatory. If we talk about backbone stiffness, then we increase the modulus and strength. Increasing stiffness also gives lower impact strength and elongation at break, because if you have a stiff backbone, you cannot elongate before it breaks. For a same, we also have seen that the modulus or mechanical properties of a polymer very much dependent on the temperature of the experiment, which means finally, when you are using the polymer in a particular application, you must remember the temperature of the application, and second, the strain rate. If you think about the application where the material will come across some load which will come at a higher strain rate, then the behavior will be different if you are talking about just simply dead load bearing capacity of a material. So, modulus and other strength or elongation at break, which means we are talking about brittleness, all these mechanical properties depends on temperature of experiment and the strain rate or the stress rate. If you compare semi-crystalline material, semi-crystalline polymer at same temperature and same rate, obviously we know that with increasing crystallinity, the modulus and strength goes up. Modulus and strength goes up. Whereas with if you cross-link this material, with cross-linking, the modulus goes up. Now, let us talk about a great dilemma in case of polymers. Now, we know that, or you can anticipate that the properties, mainly mechanical properties of a polymer materials should increase with molecular weight. It does increase and then become steady after very high molecular weight. So, basically good properties are favored by high molecular weight of polymers. So, this is nothing unusual. So, you should expect this being so that is the advantage of a polymer. So, high molecular weight it gives the high mechanical properties. Other properties do not changes with molecular weight that much, though it also increases with molecular weight, but it does not keeps on increasing even if slightly with molecular weight. The other polymer will steady it at a high molecular weight. Whereas, we have seen that you after making the synthesizing the polymer, you have to go through the processing step to make the final part. So, you must make some polymer, some molecular weight, we should be able to pass through the processing step, so that you can get the final product. And processability actually becomes easier, as you can understand, if you lower the molecular weight, lower the viscosity. So, processability becomes easier if you have the low molecular weight. So, good processing is always favored by low molecular weight. So, ease of processing will means the higher the molecular weight, it will be difficult for process. So, ease of processing will be lower with increasing molecular weight. Now, just to spend a minute why the ease of processing is so much dependent on molecular weight, just talk about the rheology and entanglement of polymer molecules. The elastic properties of linear thermoplastic polymers are due to chain entanglement. We described in last lecture that the elastic, the resistance to deformation is due to the chain entanglement, because of chain entanglement, the chains are present, other maybe intramolecularly or other chains, intermolecular chain segments are present in the vicinity of a particular polymer chain, which basically resist the deformation. So, if you have some polymer molecular weight which is polymers which are having molecular weight such a small number or such a small value that it does not entangle efficiently, then you do not get the desired property of a polymer material, which will be useful for the applications of the polymers we usually use. Entanglements will occur for polymer chains above a critical molecular weight, and we call that molecular weight as entanglement molecular weight ME. Now, if you look at the experimental value of a viscosity versus molecular weight of a polymer, viscosity till the entanglement molecular weight, viscosity increases steadily with a slope of 1, but above entanglement molecular weight, the polymer chains are entanglement. If the polymer chains are entangled, then moving past each other, going past to each other is become more and more difficult, very difficult, because they are entangled. So, the viscosity becomes much higher after the entanglement. So, before entanglement, the viscosity scales to the with the power of 1 with molecular weight, whereas the slope changes to about 3.4 after the entanglement molecular weight. So, if you increase the molecular weight further above this entanglement molecular weight, the viscosity goes up drastically, and the processing, the ease of processing become difficult and more difficult. See, always you want a polymer somewhere above the entanglement molecular weight and just above the molecular weight, so that it can be processed easily. So, this is a dilemma, which molecular weight you should make. If you make very high molecular weight, your properties will be higher. Similarly, at the same time you lose the processability, it is very difficult to processable. So, you have to have some compromise, you have to make molecular weight somewhere intermediate. So, you get the best of both. And in case of thermosets, you do not need that compromise, because thermosets are generally starts with low molecular weight polymers and you make the final product, or you process that low molecular weight, and then subsequently you cross link that to increase cross link or cure in other term, and increase the molecular weight. So, you do not have to compromise anything, whereas in thermoplastics you have to compromise between these two. You have to choose a molecular weight somewhere in between, so that your mechanical properties is just above a critical value of your requirement, and your processability also is handleable, means you can do processing. So, high enough molecular weight to get adequate properties and low enough molecular weight, so that it can be processed. So, you have to compromise between these two. We talk about continue our discussion on mechanical properties, and we come to a concept of viscoelasticity. We have seen in our discussion when we were doing this strain curve, we have seen that the curve strain curve depends upon the temperature as well as the strain rate. Now, if you think about a pure elastic material, if we stretch a crystalline solid, what happens? The energy is stored in the material, and if we in the chemical bonds, and then if you release that stress, it will come back to the original state. We talking about this is ideal elastic behavior. Similarly, if you have a liquid, then if we apply shear stress, say if I have a liquid, a glass of water and then pour it, then it will basically flow it. But if I remove the stress, it does not come back to the original state. So, in case of a liquid or a fluid, if I apply a shear stress to a fluid, energy is dissipated in flow, it basically flows and energy is dissipated, energy is not stored. So, in case of elastic material, energy is stored, in case of a fluid, energy is not stored and it dissipated in the flow. So, it is a ideal viscous behavior. Now, polymers are somewhere in between, they have, depending upon the temperature and time of straining, they vary from elastic to completely viscous behavior, and most often in the conditions they are viscoelastic. So, they have properties of both ideal solid and a viscous liquid or viscous fluid. So, polymers have both ideal elastic and viscous behavior depending on the time and the temperature. So, we call polymers are viscoelastic. At low temperature and high strain rate, polymer demonstrate elastic behavior, as we have seen earlier in our strain stress discussion, that a low temperature polymer becomes brittle, it does not elongate much. So, polymer behave elastic behavior. Similarly, at a high strain rate also, at low temp and high temperature and low strain rate, polymer demonstrate viscous behavior, and an intermediate temperature the rate of strain polymer demonstrate viscoelastic behavior. Now, you can see in this viscoelasticity behavior if you have a silly putty, the toy material silly putty in home, but I do not have that material with him. So, I have what I have a dough made of wheat flour. I just made this dough from wheat flour. I just put some water to make it soft. Now, basically what happened, this is not a ideal viscoelastic material to demonstrate, but I can show it so that you can understand what do I mean by viscosity. This is a dough made up of wheat flour, and when I stretch this slowly, what happened? It just elongates is, so basically it flows. So, it keep on increasing if I apply this stress or strain in a slower rate. So, it keeps on stretching. Okay. Now, if I apply this strain rate, high strain rate from both sides, much faster strain rate, what happened? Let us see what happened. Again I am saying this is not a example of a perfect viscoelastic material, but this is what I have in hand at this moment to demonstrate. So, I am trying with whatever available at home. Now, I have this and then I do it very fast. What happened? It just breaks. So, what happened? Again I am saying this is not the perfect material to show. If you apply the strain at a much faster rate, it breaks. It shows elasticity, is elastic behavior like a solid, but when you apply this strain very slowly, then it flows, the chains actually move past each other, it shows flows behavior and it shows viscous behavior. So, if I consider the strain stress curve, how does it look like for a viscous and elastic material? First of all, when you do tensile testing, one thing we must remember that as we do this test, the dimension of the specimen changes. So, actually the strain and the stress or the state actually changes because the original dimension changes. So, these are the terms sometimes used. Engineering stress is F force by original A, and true stress is changing, is actually basically the force by the area at given time. Where similarly engineering strain is given by dl by this original length, whereas true strain would be the L at a given time. So, that is the true strain. This true stress and this true strain is difficult to measure. So, generally we actually consider engineering stress and engineering strain all the time. Now, let us see how the stress strain behavior of a viscoelastic material. Now, let us see I apply this is stress or load. Now, I apply some time t 0 and keep at a constant level for some time and then release again, make it 0 at some t t. Now, what will do a elastic material will do? Elastic material how the stress by strain curve will look like? It will change and then go back and then how the strain will apply. The time when we apply the stress, there will be a definite strain. This strain and stress are related by Hooke's law. We will come back to that. Now, at the time when this stress is released, it will come back to the original state. and this stress and strain is related by Hooke's law they are linear and is related by elastic modulus in between as a proportionality constant. Now, what happened to a perfect? So, this is a perfect elastic material. What happened to a perfect viscous material? How the strain will changes with time. Same stress is applied, same load is applied here. So, with time how the strain will change for a viscous material. So, the time t0 it will start straining till load is present or stress is present, it will continue deform, and the time the stress is removed, it will remain deformed permanently. Okay. So, it does not come back to the original state, or there is not any recovery at all. So, this is a perfect viscous material, and here stress is linked to the rate of change of strain with time, and the proportionality constant is the viscosity. What happened to a polymeric material, a viscoelastic material? How does it happen? How does it respond with time? It basically, let me show here. Strain. So, at the time you apply the strain, it will strain to some extent and then keep on continue deforming till the load is present, and when the load is removed as t is equal to t, it will recover some part and then stay somewhere. So, it does not come back to the original source. So, this is a basically example of viscoelasticity. So, for a polymer with temperature, you can see all this behavior. Let us talk about a amorphous material. The glassy state A to B is a perfect elastic material. So, if you apply apply a stress, it will strain, and as long the stress is there, strain will be there. If you remove the stress, the strain will become 0. So, that is the example of perfectly glassy material or elastic material. So, this part glassy part will behave like a perfect elastic. What about the leathery part B to C? When you apply the stress, apply the load, it deform fast, and then as long as the stress is present, it will continually deforming, and the moment the stress is removed, it will come back, the elastic component is recovered here, and then slowly recover some of the strain, but it will not come back to the 0 strain value, there will be a permanent deformation here. So, this is example showing viscoelasticity. So, the fact that it is not coming back to the original state, it is showing some loss of energy, some viscous behavior, and part of it is actually getting recovered, which is the behavior of a elastic solid. So, that is the reason it is a example of viscoelastic behavior. Similarly, in case of rubber, a similar behavior, and in case of above very high temperature, it is like a polymer melt, it does not recover at all, and it continually gets deformed as long as stress is present. So, you get a complete viscous behavior. So, with temperature, a polymer material can show different types of viscoelastic behavior, from a perfect elastic to a perfect viscous behavior with intermediate behavior of viscoelasticity. Similar thing can be shown in case of that strain rate. With higher strain rate, it will be behave more elastic, and is very slow strain rate, it will be close to a perfect viscous, and intermediate strain rate, it will be so viscoelasticity. Now, let us move to the other properties of polymeric materials, what we discuss. We just completed discussion on mechanical properties. Now, we will talk the other properties, and again we will not go into very detailed description of these properties and how it is evaluated. We will just give brief introduction or brief description of those tests. Let us first talk about thermal properties. We discussed about the glass transition and the melting behavior of polymer earlier. Thermal properties are basically the response of polymeric material when the temperature is increased or heat is supplied to the polymeric material. Now, besides the glass transition temperature and melting point, the other behavior polymer material can show is the heat distortion temperature or the softening temperature, and very high temperature above Tm, when if you keep raising the if you keep raising the temperature, the polymer might decompose and gives decomposition temperature. So, in a generally in case of semi-crystalline thermoplastic material, you have first you have heat distortion temperature, the softening temperature, then you have glass transition temperature, then you have melting point or melting temperature, and then the degradation temperature or decomposition temperature. For thermosets, you do not have TG, you have thermosets, you have HDT and TG, and then finally the decomposition temperature. We talked about the glass transition temperature and melting point earlier. So, we want to discuss about the other thermal behavior with outer polymer behavior with temperature. This is from a practical point of view. This is the temperature where it starts softening. The polymer actually starts softening under some load. So, the heat deflection temperature is the temperature at which the material shows significant amount of deformation under a constant load. Now, this significant amount, fixed amount is basically is prefixed. So, if you compare, you want to compare between materials, you can compare with the amount of deformation, same amount of deformation between the materials. So, basically what is the test is done, that one polymer samples is specimen is taken and one load is applied, a definite load, constant load, and then temperature is slowly increased at a given rate. and at some temperature this deformation happen, and that particular temperature is known as heat and deflection temperature, and like other heat temperature will depend upon how fast you are heating up this material, how fast you are changing the temperature, and obviously the amount of load is present. The higher is the load, the lower will be the temperature, heat deflection temperature. Now, why it is important? Let me give you example. Now, these are all amorphous material, polystyrene, polymethyl methacrylate and BPA polycarbonate, and the TGs are approximate TGs are listed here 100, 145. So, looking at this material, if you say that if you make some specimen or some product out of the material, these materials will survive till around 100 degree centigrade, but that conclusion will be erratic. If we see this example, these are CD disc made from polycarbonate, and these are made from polymethyl methacrylate. Now, these were subject to a heating conditions for 96 hours at 180 degree centigrade and 95 degree relative humidity. Same thing here, but much lower. The picture is after much lower duration at 80 degree centigrade. Now, 80 degree centigrade is actually below the TG, well below the TG of the PMMA sample. So, you should expect that the polymer should survive, but when you make a part, it has its own load, it has some weight. So, it has own load, and when you stack this disc, basically the lower one will also have load from top. So, at 80 degree itself it is deforming, which means it should not be used. A disc cannot be made up of PMMA, will not survive a temperature of 80 degree centigrade. So, this is what signifies. So, if you want to make a disc and find a which will be used for an application at higher temperature, you must know the HDT of that particular material, and HDT is typically, as a general rule of thumb, is about TG minus 20 degree centigrade. So, TG is not sufficient for practical point of view, you must know the softening temperature. Now, if you increase the temperature of polymers typically degrade. This is very important in processing point of view, because while processing the polymers are subjected to a very high temperature, and as we have seen that TG plus sometimes 150 degree centigrade or TM plus 50 degree centigrade or even more, and under shear, in case of processing we are applying this melts are mixed with the screws, and so does in case of molding, which means that these undergo shear. So, polymer might degrade and decompose with those conditions. So, to find out what is the inherent thermal degradation behavior, the thermogravimetric analysis is done, which is in short called TGA. Now, TGA is basically plot of weight loss versus temperature, is just nothing but plot of weight or mass, to be precise, versus temperature. Again, the heating can be done at in air or in inert atmosphere, like say nitrogen gas or argon gas. Obviously, in air the decomposition rate and decomposition will be at much lower temperature compared to a situation where the heating is, the temperature is increased under nitrogen or argon. So, weight is plotted against temperature. Now, with we can get this information from this test. Basically, we can know at what temperature this polymer starts decomposing or degrading, and we can basically find out the temperature at which 50% weight loss or complete weight loss, whatever is your interest. Sometimes small molecules comes out of the polymer during heating, like HCl from polyphenol chloride, H2O from amic acids. So, if we can, from the weight loss, we can get some idea about whether this type of reaction is happening. We can also do isothermal TGA, where weight loss is monitored with time at constant temperature. So, basically that will give us some idea if we keep that polymer material at that particular temperature for long time, especially in elevated temperature where there is some degradation or decomposition happening or not. And at higher temperature, polymer sometimes depolymerize and which might lead to some volatile monomers. So, which we can get some idea about TGA. If fragmentation happen during heating, or as we have seen that sometimes additives are used during polymer formulation. So, if they are on heating, if there is some loss, thermal loss of those additives, that can be also found out. This is typical thermogravimetric curve of different polymers, PVC, PMA, LDP, PTFE and PI in nitrogen, and these temperatures are corresponding onset temperature and the 50% temperature. The temperature, for example, for PMA, this is the temperature corresponding to 50% weight loss. Now, the amount of mass is remaining after complete burning is what is the char. What is the char means formation after heating, and that is very important when you talk about the flammability and flame resistant behavior of the polymer. So, in this case basically it is showing that there is no char formation has taken place. The basically entire polymer is decomposed off and has gone out. If in this case for PVC there is a significant amount of materials remaining even after complete burning. So, there is some char formation has happened in case of PVC. Obviously, it also depends on how fast you are heating. So, the slower the heating, you will see the decomposition temperature at lower temperature, whereas higher heating will take it to higher temperature. Basically, polymer cannot follow the heating. If you are doing the heating in much faster rate, the polymer cannot follow the heating profile. So, the effective temperature actually becomes lower if you increase the heating rate. So, if you want to compare between different polymers, the thermal stability at higher temperature, you must compare at same heating rate. Now, there are other like thermal behavior, thermal test basically is done is like Viscous softening temperature point. It is the temperature at which a flattened needle of 1 millimeter square cross section under a specific constant load is applied, and the temperature at which it penetrates the plastic specimen to a depth of 1 millimeter, it is known as Viscous softening temperature. Another important parameter of thermal behavior is the maximum use or continuous use temperature, or it is sometimes called relative thermal index. It is the temperature, the highest constant temperature at which the material will survive related to a application requirement. What does it mean? It means that you can use how long and what is the service temperature. If you have make like that example I showed in the CD, what is the service temperature? That like means what is the maximum temperature it can survive for long duration at a for that particular application. So, if you want your CD material to survive for 10 years, then you must specify what is the temperature. You can find out what is the maximum temperature it can be used. So, you know, like in hot countries the temperature may go up to 45-50 degrees centigrade. So, if you want to survive, then your material, the maximum temperature at least should be 45 degree or 50 degree. If we talking about plastics which are used in say car bonnet, then you know that on getting constant heat from outside, the bonnet temperature may go up to 80 degree 90 degree centigrade. So, if you want to design one material or test some material which will survive the duration of car's lifetime, say about 20 years or 15 years, then you should test that in advance. So, this is done in laboratory in a accelerated way, where basically the specimens are heated in a elevated temperature with some relative humidity, and with time the retention of properties are monitored and then compared with an existing material which is already in application and for long time. So, if you compare with a material which is existing in that particular applications for long time, and if you compare your material, test material, which is as good as that particular material or even better that particular material in the accelerated lab test, then you know that your material will survive that particular temperature at least as good as the material which is in the market. Okay, let us go to the next property, which is flammability or flame and flame resistance properties of a polymer. Now, again this will be just briefed, we will have a brief discussion on these properties and subsequent properties. Basically, when you put fire on a polymeric material, it basically depolymerizes to monomer, and it degrades to combustible gas, and in the presence of heat it basically form flame and it burns. So, that is the origin of flammability of polymer material. So, if you want to decrease the flammability, you basically have to remove this combustible gas from the system, and you basically has to reduce the heat formation, heat generation on burning these polymeric materials. How the testing is done? And in the lab, the testing which is done is called limiting oxygen index. It is most versatile small scale test. It is defined as the minimum concentration of oxygen expressed as percentage by volume or volume percentage in short, in a mixture of oxygen and nitrogen that will sufficient enough to support flaming combustion of a material. Now, how long the flaming will happen, that has to be fixed for comparing between materials. Typically, it is 3-minute burning or flaming. So, what is the experiment is done? Oxygen and nitrogen are mixed, and basically it starts with pure nitrogen and oxygen is increased slowly to find out that the minimum oxygen required in terms of volume percentage in this mixture to sustain this flame for a specified time, say for 3 minutes. So, limiting oxygen index is basically the volume of oxygen required by the total volume into 100, that gives the percentage of material. Now, the other tests are also there, which are done in real applications, where basically which is been guided by UL laboratories, and the rate materials in terms of different, they gives different ratings like V0, V1, V2, HB and those things. In this case, they give the specified geometry of sample, like and these states are very difficult to carry out repeatedly, and only trained and certified person actually do test for this comparing material or give the rating. What happened? You basically take the sample and apply the flame from a particular distance, and some cottons are placed, these are cotton placed in the container below. So, if it burns and while burning the sparks comes and ignite the cotton, which basically gives lower rating. So, a sample which burn from less time and which also does not ignite the inflammable material like cotton present in the bottom of the container, they actually gives the best ranking. It basically try to mimic the applicable actual application when the polymers are actually used in application. What do you want? You want the polymers in case of a emergency. What do you want? You do not want the polymer to burn with a flame, and even if it is burned, then it should not actually gives or ignite the other material, other inflammatory material in the, it should not drip to the floor or some other inflammable or combustible material, so that the fire spreads. Also important is that it should not generate toxic smoke, that is also important. So, in case of fire resistance material, flame property, it should not burn, even it burns it should not drip and ignite other inflammable material, and third, it should not generate toxic smokes. So, these are the 3 criteria of a very good flame resistant polymer. So, objective of flame retardation, which to suppress suppression of smoke and toxic gas. It's actually a known fact that when something burns, the casualty or fatality of the people is mostly because of the toxic gases at first few minutes. So, if you suppress the toxic gas generation for first few minutes, then in case of emergency people can go out of the situation and survive, whereas if the toxic generates immediately after burning, then what happens, they cannot they actually get ill immediately and they cannot run away and find a safer place. So, strategies to flame resistance is to retard combustion process in vapor phase, and char formation causing char. If you have a polymer which forms a high level of char, typically halogen containing polymers and also inorganic polymers, and sometimes some added additives which does not ceramic additives, for example, which does not burn and just go out of the system, they actually contribute to char formation, and which actually suppress the basically prevent supply of this combustible gas to this pyrolysis zone, and thus by decreasing the flammability. Okay, we will just go to the next set of properties, where is basically the exposure. What happened to polymer getting exposed in environmental situation? For example, polymers come across different chemicals. If you are talking about medical devices, doctors or medical persons always apply some rectified spirit or ethanol to disinfect. So, your material has to survive. So, that has to be chemical resistant of the chemical the medical professionals are using. It has to be any outdoor materials, plastic material, they come every day, come across UV light, heat, outdoor heat, rain, and the bacteria and viruses present in the material. So, that is in oxygen of the environment. So, basically that combined we call that weatherability. Basically, when some polymer material or plastic material is applied, we find weatherability. Weatherability is basically combination of all these effects like rain, air, heat, light. So, combine all these we call so if a material or plastic material survives longer in that outdoor condition, it is a better weatherable material. So, we test weatherability in the lab in a accelerated chamber, which basically mimic the outdoor condition with control parameters, and we subject the experimental specimen in that condition, and after in a frequent interval we basically test their mechanical other properties like optical properties to find out whether it is sustaining in that particular weather condition or not. In case of chemical resistant, we basically apply say we actually immerse the test sample in that particular chemical agent for a particular temperature and for a particular specified time, and after that we take out that material and we measure the mechanical property change, whether it survived or not. We visually inspect the material, whether any swelling has happened or any surface is eroded or some cracking or crazing has happened, and we also see whether the molecular weight of the material has changed by the coming in contact with the chemical agent, which can be done by measuring the viscosity of material. So, what we do, we will stop here for this lecture, and we will talk about other properties like optical property and barrier property and surface property of polymers in next lecture, and we will also talk briefly that most often polymers are not used as such. They are basically used with other additives which basically protect some of the these polymers from these external agents we talk about, or it basically enhances the property which can be used from outside. So, we stop today and start with the rest of the properties in the next lecture.